Why is a diamagnetic substance? Why is a diamagnetic substance feebly repelled? Why is a diamagnetic substance repelled feebly by a magnet? By a magnet here we can consider that all the electrons of diamagnetic substance are classified into two types of electrons which rotate anti-clockwise and clockwise in a horizontal circular orbit. Say this electron is revolving anti-clockwise with a tangential velocity v. Similarly, this electron is revolving clockwise with the same angular velocity v in the circular orbit or horizontal circular orbit. The motion of all the electrons in an atom of a diamagnetic substance, the motion of all the electrons in an atom of a diamagnetic substance can be assumed to be the motion of two types of electrons revolving with the same orbital velocity or with the same angular velocity in a horizontal circular orbit of same radius but in the opposite directions but in the opposite sense, that is moving in anti-clockwise and other one moving in anti-clockwise and other in clockwise direction. When the electron revolves anti-clockwise, in that case orbital velocity of this electron, when the electron revolves anti-clockwise, in that case orbital velocity v will be acting outwards with respect to the horizontal circular orbit. Similarly, for the electron which revolves clockwise, orbital velocity, that means v will be acting inwards. As electron revolves anti-clockwise direction, in that case electron revolves in anti-clockwise direction, in that case current due to flow of this electron will be flowing clockwise direction. In that case upper face of the horizontal circular orbit behaves as south pole, lower face behaves as north pole, and magnetic dipole moment PM1 due to revolution of electron in anti-clockwise direction is PM1, which will be acting downwards. PM1 is the dipole moment or magnetic dipole moment which acts vertically downwards for this electron revolving in anti-clockwise direction, and current flows clockwise direction. Similarly, for the electron which is moving in clockwise direction, current I will be flowing anti-clockwise direction, and in that case lower face of this horizontal circular orbit behaves as south pole, and upper face, this is what the south pole is induced at the lower face, and magnetic north pole is induced on the upper face or with respect to the upper face of this horizontal circular orbit of revolution of electron. In that case, due to flow of current in anti-clockwise direction or due to flow of electron in clockwise direction, magnetic dipole moment which is PM2. PM2 is the magnetic dipole moment which is produced due to revolution of electron in clockwise direction and due to flow of current in anti-clockwise direction. the magnetic dipole moment PM2 acts down upwards. Now PM1 is equal to PM2. These two magnetic dipole moments are same in magnitude, and resultant magnetic dipole moment is PMT, which is equal to PM1 minus PM2. Net magnetic dipole moment is PMT, which is equal to PM1 minus PM2. Now these two magnetic dipole moment are equal because both are produced due to due to revolution of electron. Now PM1, which is acting downwards, will cancel out PM2, which is acting upwards, and they have the same magnitude, that is PM1 will be equal to PM2, which will be equal to PM. Now we can consider the diagram again. R is the radius of this circular orbit of the electron, which is revolving in anti-clockwise direction, and current flows in clockwise direction for this type of electron. And in this case, centripetal force Fc acts radially inwards. Centripetal force Fc, which is required for the revolution of electron revolving in anti-clockwise direction. Similarly, we can denote centripetal force Fc. Fc is the centripetal force acting radially inwards for the revolution of electron in clockwise direction. Now if we apply an external magnetic field of field induction B in vertically downward direction, we can denote the direction of external magnetic field, that is vector B, in vertically downward direction. Vector B is the external magnetic field which is acting on these two electrons of diamagnetic substance in vertically downward direction. In this case, for the electron revolving in anti-clockwise direction, magnetic Lorentz force Fm acts radially outwards. Magnetic Lorentz force Fm acts radially outwards for the electron revolving in anti-clockwise direction. So here Fm is the magnetic Lorentz force which acts radially outwards for the electron which is revolving anti-clockwise direction. For this type of electron revolving in anti-clockwise direction, as magnetic Lorentz force acts radially outwards, centripetal force Fc will decrease by a very small amount. In this case, centripetal force decreases to Fc minus delta Fc. An orbital velocity of electron revolving in anti-clockwise direction decreases to V minus delta V. So velocity decreases and centripetal force also decreases. As centripetal force decreases, that's why you can say that velocity also decreases, and in that case current decreases by delta E amount, and magnetic dipole moment which is acting vertically downwards will decrease to PM minus delta PM. Now the direction of magnetic Lorentz force is determined by using Fleming's left-hand rule, and PM minus delta PM is the final magnetic dipole moment, and this magnetic dipole moment decreases due to application of the external magnetic field B on this diamagnetic substance. And the direction of magnetic Lorentz force acting on the electron is determined by using Fleming's left-hand rule. Similarly, for the electron revolving clockwise direction, centripetal force increases to Fc plus delta Fc, and its orbital velocity in inward direction, orbital velocity increases to v plus delta v, as centripetal force increases to fc plus delta fc. And as the orbital velocity of the electron revolving clockwise direction increases, that's why current also increases to I plus delta I. And magnetic dipole moment due to flow of electrons in clockwise direction increases to pm plus delta pm. And this magnetic dipole moment pm plus delta pm acts vertically upwards. Pm plus delta pm is the magnetic dipole moment, final magnetic dipole moment due to revolution of electron clockwise direction. And here magnetic dipole moment of this type of electron increases, and 2 delta pm is the induced magnetic dipole moment which acts vertically upward direction with respect to the direction of external magnetic field of field induction vector B. Let a uniform external magnetic field of field induction B. Let a uniform external magnetic field of field induction vector B is applied perpendicular to the horizontal plane of rotation, of the electron, and directed vertically downwards. This magnetic field vector B acts vertically downwards and perpendicular to the horizontal circular orbit of rotation of the electron according to Fleming's left-hand rule. A positively charged particle experiences, according to Fleming's left-hand rule, if a positively charged particle experiences a magnetic Lorentz force Fm acting radially inwards, the electron under bracket small e revolving anticlockwise. The electron revolving anticlockwise experiences the same magnetic Lorentz force Fm. Which acts radially outwards. So here we can consider that this is plus q is a positive charge which has a tendency to move with a velocity v outwards with respect to the horizontal circular orbit of revolution of the electron. And according to Fleming's left-hand rule, central finger gives the direction of the velocity of positively charged particle, and forefinger indicates the direction of magnetic field vector B in vertically downward direction, and thumb indicates the direction of magnetic Lorentz force Fm. According to Fleming's left-hand rule, magnetic Lorentz force experienced by the positively charged particle acts towards right. Magnetic field vector B or B acts vertically downwards, which is indicated by forefinger. Forefinger indicates the direction of magnetic field B. Forefinger indicates the direction of magnetic field B in vertically downward direction. Central finger indicates the direction of the velocity or direction of motion of positively charged particle, and thumb indicates the direction of the magnetic Lorentz force. Magnetic Lorentz force acts radially inwards, or magnetic Lorentz force acts towards right. And in this case, as positively charged particle plus q experiences magnetic Lorentz force towards right, this electron experiences a magnetic Lorentz force Fm towards left. That means plus q charge experiences magnetic Lorentz force Fm towards right. This electron experiences magnetic Lorentz force Fm towards left. That means magnetic Lorentz force Fm experienced by the electron revolving anticlockwise will act radially outwards. And this magnetic Lorentz force Fm acting radially outwards decreases the centripetal force Fc to Fc minus delta Fc. Also decreases the orbital velocity, v of the electron revolving anticlockwise in the horizontal circular orbit. This magnetic Lorentz force Fm also decreases the orbital velocity v of the electron revolving anticlockwise to v minus delta v. Where delta v is the change in orbital velocity, as according to the relation Fc is equal mv square by r. As centripetal force Fc decreases to Fc minus delta Fc, orbital velocity v also decreases to v minus delta v. In the diagram for the electron revolving in anticlockwise direction, centripetal force Fc decreases to Fc minus delta Fc as magnetic Lorentz force Fm acts radially outwards. Orbital velocity of the electron revolving in anticlockwise direction decreases to v minus delta v. As a result, means if velocity of revolution of orbital velocity decreases, then magnetic dipole moment Pm is equal Ia, current into area of cross section of the circular orbit of revolution of electron, is equal to q by t, capital T is the time period, is into A, is equal to qv divided by 2 pi r into A. That is the expression of magnetic dipole moment in terms of orbital velocity v. Current I is equal to q by t, and we get the expression of dipole moment Pm. As a result, the magnetic dipole moment Pm of the electron revolving anticlockwise direction also decreases to Pm minus delta Pm, which is acting vertically downwards. Dipole moment Pm is equal to q into v divided by 2 pi r into A, where v is the orbital velocity, r is the radius of horizontal circular orbit, A is equal to pi r square, which is the area of cross section. As orbital velocity v decreases to v minus delta v, magnetic dipole moment Pm also decreases to Pm minus delta Pm. Magnetic dipole moment Pm decreases to Pm minus delta Pm, which acts vertically downwards. In the diagram, orbital velocity v decreases to v minus delta v. That's why dipole moment also decreases to Pm minus delta Pm, which acts vertically downwards. Similarly, on the electron revolving clockwise, revolving clockwise in horizontal circular orbit. The magnetic Lorentz force Fm acts radially inwards. Magnetic Lorentz force acts radially inwards and tending to increase its centripetal force to Fc plus delta Fc, and tending to increase the centripetal force to Fc plus delta Fc, and hence the velocity or orbital velocity of the electron revolving clockwise to v plus delta v. Therefore, the magnetic dipole moment of the electron revolving clockwise increases to pm plus delta pm, which acts vertically upwards. In the diagram, magnetic Lorentz force Fm acts radially inwards and it decreases. The centripetal force increases to Fc plus delta Fc, and orbital velocity increases to v plus delta v, and its magnetic dipole moment increases to pm plus delta pm, which acts vertically upwards. The vector addition of these two magnetic dipole moments, pm minus delta pm and pm plus delta pm, for the electrons revolving anticlockwise and clockwise respectively, gives rise to a net magnetic dipole moment 2 delta pm, which acts vertically upwards with respect to the horizontal circular orbit of revolution of the two electrons opposite to the external magnetic field of magnetic field induction B. That is the magnetic dipole moment in connection with the electron revolving in anticlockwise direction. That is the magnetic dipole moment pm minus delta pm acts vertically downwards. Similarly, magnetic dipole moment in connection with the electron revolving in clockwise direction will act vertically upwards in the opposite direction of the external magnetic field B, and the net magnetic dipole moment 2 delta vector pm acts upwards in the opposite direction of the applied external magnetic field B. 2 delta pm is the net induced magnetic dipole moment acts upwards in the opposite direction of magnetic field. Hence, if a specimen of diamagnetic substance or material, is placed in an external magnetic field of field induction B, an induced magnetic dipole moment under bracket 2 delta pm, an induced magnetic dipole moment under bracket 2 delta pm acts in a direction opposite to the magnetic field vector B. 2 delta vector pm acts in a direction opposite to the magnetic field vector B, and this specimen of diamagnetic substance or material is feebly repelled by the magnet, producing the external magnetic field. Induced magnetic dipole moment 2 delta vector pm acts vertically upwards in the opposite direction of the external magnetic field vector B. 2 delta pm acts upwards and external magnetic field vector B acts downwards. So this is a specimen of diamagnetic substance. This is a specimen of diamagnetic substance, and initial magnetic dipole moment PMI is equal to 0 if no external magnetic field acts on it. Now the same specimen of diamagnetic substance is placed between an external north pole and south pole. Magnetic field of field induction B0. Magnetic field of field induction B0 produced due to north pole and south pole acts towards right, and and in this case again north pole will be induced at the nearer end of the diamagnetic substance with respect to external north pole, and south pole will be induced at the further end of the magnetic substance with respect to the external north pole. Now an induced magnetic dipole moment will be acting along this direction. That means induced magnetic dipole moment 2 delta pm will act towards left in a direction opposite to the magnetic field of field induction B0. 2 delta pm is the induced magnetic dipole moment acting inside the specimen of diamagnetic substance towards left. That means this induced magnetic dipole moment 2 delta pm acts towards left in the opposite direction of the external magnetic field B0. Hence, what we can say, the diamagnetic substance will be feebly repelled by the north pole and external south pole, or will be feebly repelled by the magnets. The appearance of induced magnetic dipole moment 2 delta pm in atoms of diamagnetic substance is not affected by the thermal motion, of the atoms. Therefore, the magnetic susceptibility chi m of such materials, that means of diamagnetic materials, does not depend on the temperature, capital T, of the materials. Magnetic susceptibility is independent of absolute temperature. Chi m is plotted along vertical axis, and this is chi m versus T graph, which is parallel to the absolute temperature axis, or which is parallel to the horizontal axis.